So we can have questions where we have a step function going into some kind of RC circuit, right? And then that is fed into an OPAMP. All right, and this can be node 1, 2, and 3. And so typically the first thing is, what is HS? And HS, and usually I'll define it in the question, but it's the final output node versus the input node. So in this case would be V3 as a function of S divided B1 as a function of S. Now, many times when we're doing this, we drop off the S just to make things easier. So there's two parts to this circuit. All right. And we can just recognize that this is a buffer. All right. And yeah, you know, it's an ideal, unless you're told otherwise, OPAMP is ideal, right? And you can go through a derivation, but really it's ideal. There's negative feedback, right? And that means V plus equals V minus, right? And then that will give us V3 equals V2. And notice I dropped off the S, right, just for convenience. The other part of the circuit is the RC time constant part of the circuit. And really, voltage division. But first, before we do that, we convert this to, we kind of take the Laplace transform of the whole circuit. So I'm just going to say the Laplace transform of that circuit is going to be, now instead of this, which is like a time domain symbol, it's 1 over S, right? Because that's what a step function becomes. R is still R because pure resistances have no frequency dependence. And the capacitor, we use an impedance and 1 over SC. All right, and we have node 1, node 2. Now, with voltage division, we can just put ZC, ZR plus ZC, all right? And this is V2 over V1, right? That equals 1 over SC times R plus 1 over SC. What we do is we need to get this into a proper polynomial format, okay? Well, this is mathematically true. It's kind of hard to do a Bode plot from it. So we'll multiply through by S, and we'll get C SR plus 1 over C. And then what we'll do is we'll take out an R from here. So we get 1 over RC, S plus 1 over RC. And now this is a format that we can start to work with, but we can even make it easier when we say omega naught, or the cutoff frequency, equals 1 over RC. right? Then V2 over V1 becomes omega naught S plus omega naught. And right now, that's where our pole resides. All right. So that would be, so then we just have to find the final transfer function, which is HS equals V2 over V1 times V3 over V2. Since the scale factor was just 1, we really just get, in this case, omega naught S plus omega naught. So that's the transfer function, right? Let's see. I want to add some grid lines, then, because we're about to do the Bode plot. Wait, I hear something, but I can't. I can't quite hear. Hey, are you talking or are you asking a question? I can't hear. Is that you, Victor? Victor, are you talking in the background or? Hello?
Hello? I just muted it, sorry.
Oh, okay. Sorry to. I just don't know if you have a question or not. All right. Okay. So now, let's move on to the Bode plot. And yeah, as time goes on, these will get easier to do. So we're plotting omega, which is radians per second. And, you know, I can recognize that this is a low pass filter, right? If I let S equal 0, HS will equal, you know, it's approximately equal, omega naught over omega naught equals 1, which is 0 dB. And if I let S kind of go to infinity, now it's not really S, it's really J omega. All right. And that, if I let that go to infinity, HS goes to 0. So that's how I remember that it's a low pass filter. All right. So, and this low pass filter, right, when this is 0, you get omega naught divided by omega naught. And so really it's going to start at 0 dB. Now, if I had a gain term here, it would just be, it would start at whatever gain that was. And then there's going to be some omega naught, and it's a first order, so it's going to, the slopes are going to be in steps of 20, right? So for the asymptotic magnitude plot, I come up to omega naught, and omega naught times 10, omega naught times 100. All right, so I go over 1 and down 20. All right, I go over 1 down 20. Now you can see that it can be kind of hard to draw this, but really what's easy to check is the DC gain right? Is the break frequency at omega naught, whatever it's calculated? Now, the slopes can be a little bit sloppy to draw, but really, if you just put in minus 20 dB per decade, then I know that you know how to draw a first order low pass filter. Because in grading, I look here, and I look there to make sure that everything, and of course the plot's got to be going in the right direction. Then for the phase, what I like to do is have omega naught divided by 10, omega naught times 10, and a low pass filter, first order low pass filter, right? There's S, right? S to the 1, right? That's first order. S squared would be a second order, and so on and so on. So it's the transfer function, which, yeah, I'll rewrite, is this. It's first order, right? There's one pole there. So that's going to start at 0 degrees phase. Oops. And at omega naught divided by 10, that's when it starts decreasing. At omega naught, it's minus 45. When I get to 10 times omega naught, I get that. All right. So that would be, how I would do a low pass filter. Now, yeah, this is a lot easier to draw than one of those Bode plots, like that might be question 2, where you have S plus 10, divided by S plus 100, S plus 1,000 times some constant, right? Those Bode plots take a little more. You kind of do each one separately and then sum the results. But for a high or a low pass filter, it's as easy as finding omega naught. That's where it goes. And for first order, it's minus 20 dB. And for every order, right, you get a minus 90 degrees phase shift. All right. So like on another problem, if I squared that and squared that, I would get the same looking plot, except now the phase would be the magnitude would minus 40 dB per decade, right? And actually what I'm going to do is put this in red just by squaring it. Now you know that red means that's changed. And really, I would get the same thing, except this would be minus 180, and that would be minus 90, and that still stays at 0. So the low and the high pass, once you got those down, they're pretty straightforward. Now we need to come up with V3 for time. Well, that's going to equal the inverse Laplace transform of HS times V in of S, which equals omega naught S plus omega naught times the step function. And really, you just look this up in the table, and this is going to be 1 minus e to the minus omega naught t. Then the final part is we need to plot this. Okay, and this kind of plot is an asymptotic approach, right? And it's going to take 5 tau to get there. Scale is from 0 to 1 volts, right? And yeah, if it's you're wiggling around a little bit, that's okay. I can understand that. So that's about 5 tau. In this case, what is tau? Well, remember, omega naught equals 1 over RC equals 1 over tau, right? So 5 tau will equal 5 RC. So you just take the value of the resistance times the capacitance, multiply it by 5, and just draw that out, right? And this is in seconds. And that would be that whole problem. Usually the other version is high pass. Any questions on that? And I'll post the video.
Go away.
So let's try to review what's going on with these imaginary numbers and phase. Okay. So this is the imaginary axis, and this is the real axis. And let's just plot a point. 1 plus j. So I go over 1. I go up 1. And so that's my point. And you can see that my angle would be 45 degrees, right? Because the phase is the imaginary part divided by the real part. All right. So what if I had 1, oh, I want a different color. What if I had 1, 0? So that puts me here. I don't go up any. And you can see, yeah, the phase is 0 degrees. All right, so that's the first point. This point here would be where omega equals omega naught. This would be where omega equals 0. Now, if I plotted the point 1, 2j, right? So I go over 1, go up 2. I can see that the phase is higher than 45. If I plot 1, 10j, right, where it's this is 10 times that. All right, so I'm over 1, 1, 2, 3, 4, 5, 6, 7, 8. I have to scroll up. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So I'm over 1 here. Okay. Now you can see my phase is getting close to 90. Now what if I plotted 100J, right? Well, then that goes right off the screen, and it's really going to be practically 90 degrees. So when we look at the phase low pass, right? Well, okay, let's take HS equals omega naught S plus omega naught. Well, the top part here, if I were to convert that into phasor notation, the magnitude is omega naught. It's all real, so the phase is 0. Here, let S equal J omega, right? What I get is a magnitude of omega squared plus omega naught squared. And then the phases arctan omega divided omega naught. Now this, right, was the magnitude Bode plot, and we already did that, right? We're just worried about the phase. And so in our previous example, we went from 0 to 45 to 90. So we have 0 where omega equals 0. We have 45 where omega equals omega naught. And then we have 90 for omega greater than omega naught. So we have 0. This is in the denominator. So 0 minus 0, 0. 0 minus 45, minus 45. 0 minus 90, minus 90. And then it just gets stuck there. Just like I drew here. Okay? How's that?
I have a question. Where you have V3 of T equals inverse Laplace. What is where is Vn at, or that just be the step?
So I'll just redraw that here. Here's the step, right? Which is Vn, which is node 1. And yeah, in this case, Vn equals V at node 1.
Okay, I get it.
Yeah, sometimes I make, I start going so fast that the shorthand gets a little destroyed. Okay? And so just as recall, this is time. And then if I write, 1 divided by S, Vn plus minus 1, this is Laplace or S domain. And really the Bode plot, right, it's the magnitude of the transfer function where S equals J omega and the phase of H of S equals J omega. Remembering that S is a complex quantity where you have the imaginary and the real, and S can be anywhere in here. And if you think about it, the Bode plot is the S-plane, but just along that axis, and this would be the minus and the plus, but we only do the positive axis. All right, if that helps.
Can the voltage for the step response be a very high number, or is it usually capped off at a number that's not too large?
So the step function?
Or like exactly the graph of the step function. Because on the homework last night, I
Okay.
got like I don't know,
For
like
the input or the output?
for the output, I believe.
Okay, so
You know, when we
all right, U of T, right, is, you know, T greater than equal to 0, it equals 1, else 0. But, you know, that can be scaled, all right? So let's say in the previous example, I do this. I think 1K, 99K, right? Now, everything's the same except now it's 100 times 1 minus e to the minus omega naught t. The Bode plot, right, rather than 0 dB and coming down at omega naught, it's really 20 log of 100. So this would actually start off at 40 dB, right? Now, that being said, you say, hey, I put in a volt and now I'm swinging up by 100. And yeah, I would say for normal op-amp circuits, their power supplies are limited to, you know, I usually see at most plus or minus 15. Now, I didn't give a power supply and I said it was ideal, and that means it can go to whatever you want it to go. But if you were a real test engineer trying to do this, oh, you would have to have, instead of 1 over S, you'd probably want 0.01 over S so that you would get a 1 volt out to measure. So your instincts are right, but for the question, you could put it in like that. Because, yeah, you're probably trying to use your knowledge of a physical system to make sure you're on track. Which is a good thing.
Right. Yeah, thank you.
Yeah, that's a great question. And on an interview, if you came up with this and then you said, yeah, that's the answer, but the op amp is probably going to limit it. And that was like on homework 2, where I showed when that would happen. But I said, oh, the power supplies are limited by this. I put down the conditions so that you could figure it out, right? If I said, if you built this circuit, oh, that's quite different than here, what's the theoretical response of it? Okay. Any other questions?
Can we just do an example of a convolution?
All right.
Like a hard example, because I get the easy ones, but I get stumped on on the tougher ones.
Well, you
But
know, it's funny because they can all become hard rapidly. Let's see. All right, I have one in mind. So let's do G of t equals RT minus 2 minus 2 RT minus 1 plus okay, which goes up, comes down, stays flat. And let's do H of t UT minus UT minus 4. All right, so that should give me here 1, 2, 3, 4 down. Now, you know, I believe, you know, that there's always more than one way to do something, and I don't necessarily want to tell you what the best way is for you, but I really do believe that the Laplace transform method's pretty good. But what sometimes can happen is you'll get some equations and the equation's right, but then folks really misinterpret how the plot is supposed to go. So what I like to do is put it in like this and then almost do a time domain convolution in my head, right? So that I can make sure that I plot what I want to plot. And so all I do is I draw this picture, right? Then I'll draw, and these functions are symmetric in time, so it doesn't matter that if it doesn't look like I flipped it. And so I'll just do this, right? And first thing I notice, in this particular example, starts at 0, ends at 0, starts at 0, goes up to 1, and ends at 0. So the thing is the output, it's going to do some things, and it's going to end back at 0, and the time it takes to do all of that will be the sum of those two times. And it comes out, but that's just something to consider. All right, then I'll just start drawing what I think are the important parts. Well, there's no overlap here, so it's not really, so I'll draw it until there's something's overlapping, right? And then I say, well, the area in question, right, is this times this integrated. So I have something that's a constant, and I have something that's linear. So when I integrate that, I've got to get some kind of t squared divided by 2. Maybe it's scaled different, maybe it's delayed, but there's something like that there. Then the next spot, or the next kind of maybe area of interest, is now here. Now, this part, that area, right, this overlap is always the same now. It's like a constant. But the area, if you notice, is this is still linear, but the area is getting smaller, all right? So here the area should be increasing parabolically, but then the area is going to get smaller, all right? So it doesn't go up forever. Then I have another region of interest where as this moves along, the overlap is the same. So it's going to have an area of, it's going to have a constant area. So it should, the convolution should be constant. Then it's going to leave in that same kind of way. All right, so
is that shaded part basically like a constant?
For right here, yeah, as this moves this way, right, this overlap, this times this is constant, right? Then as the tail end starts to leave, right, you know, first it'll be, no, this is happening. You know, first it's overlapped all, then it starts leaving, and so then it's changing. And so really it's just symmetric. So really it's going to go up, it's going to come down. And let's just see, there's this region here where nothing's going on. Here's the first non-zero region. Then here's another region of non-zero. All right. Then here's another region of so this is increasing. This is increasing, but not as fast. This is flat, right? And then there's two regions in here that I described. So I'm thinking that there should be 5 regions. Now I might have made a mistake because there's 1, 2, 3 times here, 1, 2 times here, but 2 of those times are happening at t = 0. So really I should have 5, there's 5 different times going on in here. My final graph should have 5 different inflection points or something. All right. So now, okay, now I know what it should look like, because when you do the Laplace transform, it's easy, it's mechanical, but you can rapidly kind of forget what's going on. All right, so the Laplace transform of a ramp at time = 0, 1 over s squared. 2 times a ramp with a delay of 1 gives me this. 1 times a ramp gives me this with a delay of 2. I might have called it h of s, I forget. So that's ut gives me 1 over s minus 1 over s with now that's delay was 4. So f of s equals g of s times, no longer convolution, h of s, okay, and 1 over s squared minus 2 over s squared e to the minus s plus 1 over s squared e to the minus 2s multiplied by 1 over s minus 1 over s e to the minus 4. So remember I said there should be there's 6 things, so there should be 6 times, but this times this, like this has a different delay than this has a different delay than all the others, but this delay is still the same thing. It's still it's like e to the 0, right? So I get 1 over s cubed, right? Then I get minus 1 over s cubed e to the minus 4s, right? Here I get minus 2 over s cubed e to the minus s. Then I get plus 2 over s cubed. So s, 4s minus 5s. This gives me plus 1 over s cubed e to the minus 2s. And then we have the final part which is minus 1 over s cubed minus 2 minus 4 minus 6s. Now really, then I like to organize things in order that they happened. So this is 1 over s cubed. The next thing is I just have a delay of 1. So that's minus 2 s cubed e to the minus s. I have a 2s, so plus 1 over s cubed e to the minus 2 s. I have 2. The next thing is 4. The next thing is 5. And the next thing is minus, wait, lost track. Now notice this thing right here, minus 6x, right? That's when we said that this will be non-zero for T1 plus T2. Well, this was 2 units long, and this was 4 units long, and we can see just by the fact that the last thing is 6, which is, minus 2 minus 4, gives us the right answer. Okay, I don't want to have to rewrite all of that. So V or F of T is going to equal the Laplace transform of all of that. All right. And this 1 over s cubed becomes t squared divided by 2, and you just look it up on the table. But remember, when we did our intuitive integration, that's what we were thinking, right? Now, something important here is when you look at the Laplace table, it just shows you this, right? You've got to put in the UT, right? Because this is the real shape of t squared divided by 2, all right? we remember when we took that Laplace transform, it was a step function, right? The ramp function has a step function in it. So it's 0 before time equals 0, and then it comes up. So you got to have that right there. Now the next thing we have -2, right? And divided by 2. And it's going to be same thing. It's going to be t, but that delay there, right? You put the t, you have to put the delay in as well, and then square it. And then you've got to put the step function there as well. Then we have t minus 2 squared divided by 2 u t minus 2, right? Another minus sign. So we have t minus 4 squared divided by 2 u t minus 4. And I've run out of room. So then I have plus 2t minus 5 squared divided by 2 ut minus 5 minus t minus 6. Now, this part, this is really hard to draw by hand, all right? But before we draw it, right, what's this? That's just RT squared divided by 2. This is minus RT minus 1 squared, the 2's have canceled, plus RT minus 2 squared divided by 2 minus RT minus 4 squared plus RT minus 5 squared, 2's have canceled, minus T minus R T minus 6 divided by 2. Now, this can be really hard to see that effectively, that's really the shape that you're going to get, all right? And yeah, for something that complicated on an exam, I'd probably, do you get this shape, right? And really, here, okay, here we just have like an increasing exponential. But then at time equals 1, right, it doesn't bring it to 0 like when you're doing the ramps where you just keep track of the slope, but it just slows it down. I need a better color. All right, it's slowing it down. But what'll happen is this will keep going that way. So you need something to now, I'll keep it I guess I'll just keep it green. I need something to counteract this from going too far. So this was 1, this was 2. Now it's going here. And at 4, it's going to go down again. And yeah, it's going to look parabolic, right? And at 5, we have to soften that slope a little bit. It's going too sharp. We need to increase it. Oops. I'm sorry. Where are we? 4. So 4 will make black, right? I guess I'll do a highlight in yellow. So this, if left alone, right, if we don't do anything about it, it'll just keep going down, right? So we need to kind of bring that back up. Well, the yellow does that, but it will keep going back up if we don't do anything about it. And I'm going to go back to red. So that means we need to subtract something from this at 6, which keeps us there. All right. Now, I think this one's a little bit more than what I normally ask for on a on an exam. But there's one way to go about it, is that if we have t, right, and we just have 0, 1, 2, 3, 6. So we have to go at least till 6, right? So what's our function really that we're worried about is RT squared, right? Which I guess I'll just put a 2 here, right? So at time equals 0, that's 0. 1 squared divided by 2 is 1/2. 2 divided by 2, or no, 2 squared divided by 2 is 2. 3 squared is 9 divided by 2. 16 divided by 2 is 8. 25 divided by 2, 18. 49 divided by 2, and 32. All right. Now, the next thing is minus 2 RT minus 1 squared. Well, the thing is this and this are really the same, except it's just delayed and multiplied by 2 and inverted. So time equals 0, you're going to get the same thing, right? But this is delayed by 1. So when I'm at 1, 1 minus 1 is 0. That gives me 0. And so this goes to 1. This goes here, but it's 2 divided by 2, right? The 2 goes here, so it's 9 divided by 2. Oh, wait, multiply by 2. Sorry. Yeah, this is right. 2 divided by 2, right? This would be, this would just become 9. And, wait, no, 2. No, this one's 4. 9. And you can start making this table. And yeah, it gets really involved, right? And you can keep just delaying and scaling and then kind of summing all these functions. That, maybe for homework, that's the way to go. another thing is if I go back to my step function and I'll just do you know what? That's not 2. I don't know where that 2 creeped in. I'm sorry. It's not 2. And then plus t minus 2 squared u. Now here's the thing, right? T greater than and greater than or equal to 1, right? The function is really t squared divided by 2, and that's our exponential. Between 0, between 1 and the next value is 2, right? I still have this, but that's 1, right? So I can kind of get rid of it. Then I have minus t minus 1 squared ut minus 1, right? But because of our time frame, that's 1. Well, for this time frame, I have t divided by 2, then I have minus t squared minus 2t minus 1, right? No, plus 1, all right? Then I'll have t squared divided by 2 minus t squared plus 2t minus 1, and then I'll have minus t squared divided by 2 plus 2t minus 1. So between this region, this is the actual thing that you would plot, but it's only valid in that region. And you can see, whereas before, I was going up quadratically, now I'm slowing down quadratically, but I still have a linear, I don't come to a complete halt. But if t goes on long enough, this will overpower that. All right. Then between t greater than 1, no, that's the one I just did, 2, and then I believe the next one is 4, right? I still have t squared divided by 2. I still have t minus 1 squared. I still have, or in addition, I have t minus 2 squared. Yeah, 2. ut minus 2. But again, where we are, this step function is just 1. And so I get t divided by 2 minus t squared plus 2t plus, minus 1. And here I get t squared minus 4t plus 4. So now, right, now if you look at this, the quadratic part will be slight, it's hard to see, but this actually balances itself out. It should, oh, divided by 2. So divided by 2, divided by 2, divided by 2. When you work it all out, because yeah, it's increasing, it slows down, and then it should flatten. All right. Still, that is way really too hard, which is why for this kind of problem, yeah, I look at it intuitively and say, well, it's going to be exponential, then it's going to slow down. I mean, it's going to be quadratic, then it's going to slow down, then it'll flatten, and then it'll just do the inverse. All right. Because on an exam, I assume you don't have a graphing calculator and things like that. Now, yeah, some problems, yeah, like if you're doing, rectangles times rectangles, yeah, you should be able to do. The easier the function, the more exacting your response has to be. All right. You wanted a complicated one, but that might have ruined your confidence in the whole thing because it's so complicated we lose sight of what we're doing. Okay. And I got to go back because I might have made a mistake somewhere because this really should. So that's 2t, that's minus 2t. That cancels out. T squared plus t squared minus t squared. All right. That cancels out. And then I'm left with a minus 1. And 4 divided by 2 is 2. So 1. So actually, yeah, it leaves a constant of 1 in that region, right? There's all these t's will cancel each other out. It's 5 o'clock. That's about all I think I have time for. But is there any quick questions? Is anybody left? No, we're all here. All right, then. I'm going to post this right away. If you're not in my, you know what? I'll just send out a link from Canvas, but it should be in my, my YouTube channel. All right.